Hello, welcome to video 21 in the lecture Advanced Mathematic Modeling. So now in our explanation of all this probability theory and so on, so we are still not finished with the fundamentals. I still have to describe one important thing, that's multivariate distributions. So I know you probably, as me, also want that we now enter dynamical problems where probabilities depend on time, where we really have processes in time. So we need to cover one other basic thing. But maybe when you look at the examples that you get in the exercises, you see that already with the framework that we developed so far, we are already in there. We have the possibility to treat some interesting applications, but in order now to get there to time-dependent problems, we need to have multivariate distributions, because we need to be able to characterize random numbers which differ in time. So we need to know what's the distribution of different random numbers, and that's what we're doing now. Okay, so far random numbers were scalar values. So what is if the random numbers are vector? Let's say we have a vector of random numbers. So we have here vector x, and we have random number 1, random number 2, until random number r. Yeah? And also when we have r random numbers, we can associate these r random numbers a probability, and then we say we have the probability that the first number is x1, the second number is x2, and so on until xr. And this we call the joint probability distribution. So there is actually nothing special here. It's just that the distribution does not depend only on one variable, but it depends on r variables. And then by normalization, so I wrote this here for continuous variables, this can also be for discrete variables. And normalization, now we need to integrate over all these variables, integrate over dx1, dx2, integrate over dxr. Our probability, which depends on x1, x2, until xr equals 1. So that's the normalization. So that is really a probability distribution. And now there is a way, if you have a distribution of r numbers, you can integrate over just some of them. Then you end up with a distribution of less variables. So let's assume we have a subset S, which is smaller than r, a subset of S variables. And then we can define a marginal distribution. So we define a distribution which depends on the subset, which now goes only from x1 until this xs, so the first s variables, and we obtain this if we integrate our full distribution, which depends on all variables, the first s, and then xs until xr, so that's the full distribution, and we integrate over dx s plus 1 until dxr. So we divide our probability distribution, the first s, and the remaining r minus s, integrate over the other ones, and then we have just a distribution which depends on s variables. And we call this the marginal distribution. So usually when we have we need only distributions of two random numbers, and so we have a distribution of two random numbers x and y. If, for example, we integrate over dx, and then this is something which depends only on y, and this we call the marginal distribution of y, which depends only on the variable y. Okay, so that's marginal distributions, multivariate distributions. And now with these multivariate distributions, of course, we can characterize them by expectations values as usual. For example, we can write down the moments. So we can take the first variable to power m1, second variable to power m2, and so on. The rth value to moment x power mr. So that would be one moment where we have multiple exponential functions, and we calculate this in the normal way, that we have our probability distribution and multiply it with x1 to m1, x2 to m2, and so on, times our marginal our probability distribution from x1 until xr times the x1 until the xr. So just the normal way how we calculated moments before. And for example, we can, if we always have the simple distribution of x and y in mind, so so if we have such a distribution, so what's then the expectation value just of x? So we need to integrate x, p of x, y, and we need to integrate over dx, dy, and you see we can write this just as integral of x, the marginal distribution dx. So you see this is also the expectation value. Yeah, so the expectation value of the distribution which has just one variable of the marginal, there's just the marginal, the expectation of the marginal distribution px. Yeah? Okay, so we can calculate moments. Now we have a definition, and that's the independence. And then we say this variable x and y are independent if p of x, y equals the marginal distribution of x multiplied by the marginal distribution of y. So that's just a definition. And now if we have two random numbers which are independent, then the this moment, so the expectation value of x times y, is equal to the expectation of x times the expectation of y. How can we prove this? So we just calculate this. So we calculate expectation xy. This is given as the integral dx, integral over dy, x times y, p of x, y. And now now we can just use this here, we can rewrite this as the marginal distribution, as the product of the marginal distributions, and then we have here dx px of x, and then we have this integral dy py of y, and this is just the product of the expectation values. So that is very simple to prove. Now, so this was something about the expectation value of a product. Well, we have a formula in the moment only if the variables are independent. What's the expectation value of a sum? So, and then we want to know what's the expectation value of x plus y, and yeah, just simply put in these definitions, and then you directly see that's the expectation value of x plus the expectation value of y. So that's very simple to show. So the expectation value of a sum we can write down very simple. Is there a formula for the expectation of a product which also works if the random numbers are not independent? And in order to come to this, let's do some deviation and first calculate not the expectation value of the sum, but calculate the variance of a sum. How do we get this? So we want to calculate the variance of the sum of x plus y. So what is the variance? So the variance was the expectation value of x plus y minus the expectation of x plus y, and this needs to be squared. This was just the definition of the variance. And we have also how, if you now work this out, then you see that we can write this x as the expectation value of, so here x minus the expectation value of x, because the expectation of a sum is the sum of expectation values, and then we have plus y minus the expectation value of y, and this still needs to be squared and the expectation value. And now we work out yeah, just this product here, and then we can write this as the expectation value of x minus expectation value of x squared plus the expectation value of y minus expectation value of y squared plus 2 times the expectation value of x minus the expectation value of x multiplied by y minus the expectation value of y. And now you see this here, this is just the variance of x, and this is the variance of y. So the variance of a sum is the variance of the first term plus the variance of the second term plus 2 times something what is left over, and then we call this here the covariance. So we say, okay, so that's the variance of x, that's the first term, plus the variance of y, which is the second term, plus 2 times the covariance of x and y. This means that this combination here, we say that's the covariance. And so far that's just the definition. And it turns out this covariance, so this combination which here naturally emerged, that's the crucial ingredient that we are, or the crucial moment that we need to consider when we have two random variables, so distribution of two random variables. So as we said, in principle, for distribution of a single variable you can calculate all kinds of expectation values and moments, but we just need the first, the second moment, and variance and standard deviation. And so when we go to a distribution of two variables, the only new thing, the only important thing which we in practice need is this covariance. So let's write this down. So the covariance of x and y is then defined as this expectation value of a normalized x variable. So we subtract the mean of x and then we multiply by a normalized y, and from this we need the expectation value. And now if you work these terms out, then you see this is exactly the difference of the expectation value of the product minus the expectation value of x times the expectation value of y. And here you directly see this is symmetric, so the covariance of xy equals the covariance of yx. That's the covariance. And so now what can we do with the covariance? Maybe some properties. If x and y are independent, then we have that the covariance of x and y equals 0. Why is this the case? Because we said when they're independent, this expectation of the product is the product of expectations. The covariance is just the difference. So for independent random numbers, the covariance is 0. But we cannot revert this. If the covariance is 0, we cannot conclude that the random numbers are independent. So we cannot say covariance x and y equals 0, that x and y would be independent. So this does not work in general, which is a problem, because like the independence of two random numbers is a concept which is not so easy to establish. The covariance is something we can easily compute. It's just an expectation value. So if we want to know if two random numbers have something in common, we typically calculate the covariance, also when we analyze data. And then if the covariance is 0, then our intuition says, oh, they're independent. But that's not true. So very often we say in science, correlation does not imply causation. So if two things are correlated, we don't know that they're really mechanistically connected, or if two things are not covariant, we don't know that they're independent. Let's give you an example. let's take y equals x squared. Yeah, now assume that we have the marginal distribution px of x. This should be symmetric. This is the same as px of minus x. So let's say here's x, and then we have y, and they're related like this. So and now we assume the marginal distribution is symmetric around x, and then you see but y is only positive, and then you see that the full distribution cannot be written as the product of the marginal distributions, but if you calculate the covariance of x and y, so this would be the expectation of x to power 3 minus x times expectation x squared, and now since this distribution is symmetric, but you have a power of x which is an odd number, so this is 0, and the expectation of x is 0, so the covariance is 0, but you cannot so these random numbers are not independent. Yeah? So we cannot conclude in general, if the covariance of two random numbers is 0, that the random numbers are independent. So now one thing about the covariance. The problem with the covariance is it's not a linear operator, or the variance also is not a linear operator. So if you have the variance of a times x, so you scale a random number by a scalar a, so you can easily show this goes a squared with the variance of x. So the variance is not a linear operator. And the same goes for the covariance. But sometimes when we want to analyze data, we want to normalize our measure so that it's independent of the variance of random numbers. So then what we introduce, so we introduce this rho of x and y, and that's the correlation. So that's the covariance of x and y, which is normalized by the standard deviation of x times the standard deviation of y. Yeah. And this is the correlation coefficient. Yeah. And now we have normalized the deviation of x and y. So this means so if you, for example, if you have the covariance of a variable x which is scaled by a, and you have the covariance of a variable y which is scaled by c and then added by d, and so this is equal to a times c mal the covariance of x and y. So if we just scale, so if the individual variable x and y scatter a little bit, this is increasing the covariance here by this factor. But sometimes we want to know is the amount of covariance, does it depend on the relationness, the relation between the variables, or just the scattering of variables? And then if we normalize the scattering out, and we get the correlation coefficient. So the correlation coefficient of a scaled variable and a scaled y variable is just the correlation coefficient of the original variables, and the only thing what can happen that you have a minus sign. That might happen so that you have to, so the absolute value is the same, but maybe the sign is there. So this means the correlation really got again out of the viewing window. So if you take the correlation of scaled variables, this is the correlation of the original variables, maybe multiplied by a minus sign. So for data analysis perspectives, we always usually want to calculate the correlation coefficient, and I assume everybody of you has seen the correlation coefficient. But for calculations, if we don't analyze data, then usually we calculate the covariance, because that's the fundamental quantity. And sometimes in the language we don't really distinguish between this. So for example, here I already said correlation does not imply causation, even though I spoke about the covariance. Yeah. So sometimes one speaks about correlation but means covariance actually. Yeah. The difference is just a normalization. And I think you all know from data analysis, if you have two random variables, x and y, you want to know this cross correlation coefficient, and then you have for sample, so you have points, and so if in general you have here a relationship, so that you can have a straight line with a certain slope, then this gives you the correlation coefficient between the variables. If this is a negative tendency, then you have a negative correlation, and if this would be here in a circle, you would have correlation 0. So that's all what we need to know about multivariate distributions. So what we have to keep in mind, we characterize the relation of two different random numbers by the covariance, and sometimes it's important to see how this is worked out, how it's calculated. So I will show you now two simple examples how we can really calculate covariance and marginal distributions for two distributions of two random. So first, let us calculate the uniform distribution on a rectangle. So here we have a plane with two random numbers, x and y. We assume both are positive, and we say the probability distribution is just a constant, and it's normalized by 1 over a times b. If we have here the value a, here the value b, and the distribution is just in this rectangle. So this is normalized, because if we integrate over the whole rectangle, the area is a times b, and so if we have here this value of 1 over a times b, so that's really normalized to 1. So what are the marginal distributions? Calculate the marginal distribution of x. So we have to integrate over y, p of x, y, dy, and y goes from 0 to b. And so we have just a constant, we integrate this, and this just gives 1 over a. So we also obtain the uniform distribution of the x variable, which is just uniform in the interval between 0 and a. And similar, of course, we calculate the marginal distribution of y is just 1 over b. So now let's see what is with the product of the marginal distributions. If we have px of x multiply with py of y, so we multiply these two distributions, 1 over a times 1 over b, and we see that's the full distribution. So we see this is the same as p of x and y, and so that means x and y are independent. independent. So if we have a uniform distribution on a rectangle, x and y are independent. So now what's with the covariance? Let's calculate first the expectation of x. So we know that's the expectation of the marginal distribution of x between 0 and a. And now the marginal distribution is 1 over a. So we have 1 over a. Now we have here integral over x. So this gives 1 over 2 x squared, and the borders between 0 and a. And this is a over 2. So we see here that's the expectation value of x as it should be for a uniform distribution. And in the same way, the expectation value of y is here with b over 2. So also expectation value of y equals b over 2. So what's the expectation value of the product? So we have to integrate over a, we have to integrate over y. Now we have x times y, the probability distribution 1 over a b, and we integrate over the x and over the y. And then you see you can separate this. First we integrate x over a dx between 0 and a, and then we integrate y over b dy, and this just gives us a times b over 4. And you see this is the same as the expectation value of x times the expectation value of y, and so we see the covariance of x and y equals 0, which is, of course, it should be because we have independent random numbers. So, oh well, here again, so the expectation of x times y equals the product of the expectations, and so the covariance is 0, and it should be like this because the random numbers are independent. So now take another example which looks very similar but is slightly different. Take a uniform distribution. So here we have this example, we have a circle, it's constantly you have a uniform probability, the circle has radius 1, so normalization now requires that p of xy is 1 over pi, and here x and y can be positive or negative. And so you might wonder what's the difference between this example and this. So let's calculate the marginal distributions. So px of x. Now we need to integrate 1 over pi, the distribution, we need to integrate over dy. And now if we integrate over dy, now you have we integrate over such an area. And then you see the borders here go from minus 1 minus x squared to plus square root of 1 minus x squared. So if we work this out, then we have 2 over pi times 1 minus x squared. So actually it's not a uniform distribution anymore. So it's a distribution, if this is x and we want to know what's the marginal distribution px of x, you see it's the distribution is like this, so it's not uniform anymore. And similar, the marginal distribution of y equals 2 over pi times 1 minus square root of y. And it's clear that the marginal distribution is not uniform anymore because we have much more probabilities for small values of y than for large values of y. So now let's see if the variables are independent, so let's multiply these two marginal distributions, px of x times py of y. So we multiply this equals 4 over pi squared, probably 1 minus x squared times 1 minus y squared. And we see that's definitely different than 1 over pi. So that's very different than here the joint distribution. And this means x and y are not independent. They are dependent. And how do we see this intuitively? We see this intuitively because if x has a larger value, then I know precisely the value of y. Then y must be 0. Or if y, if y is very large, we know that x is 0. So there is some dependence. Here it's not the case. If x has a large value, we have no idea what y should be. Whereas here, if x is large, we know y is 0. So that's the difference between independent variables and dependent variables. So, but now what's with the covariance? Let's calculate first the expectation value of x. So we need to integrate. We integrate over x. So minus 1 to 1 x, the marginal distribution of x dx. So the marginal distribution we had here. So we have 2 over pi, integrate from minus 1 to 1 x times 1 minus square root of x dx. And by symmetry you see this is 0. In a similar way we have also the expectation value of y equals 0. And that's also clear. I mean, the marginal distribution is symmetric, so the expectation is 0. Or here in the circle, the expectations are 0. So now let's see, what's the distribution here of expectation of x times y. So now we need to integrate. We integrate x from minus 1 to 1. And now we integrate y. And that's the same that we had here. Now we have to integrate y over a smaller range. So we integrate from minus square root 1 minus x squared until plus 1 minus x squared. So that's the ranges. So then we have the probability distribution 1 over pi. And then we have to integrate times x times y and integrate over dy and integrate over dx. So and then, so let's do the y integration. We integrate over minus 1 to 1. So then we have x over 2 pi and then y squared between the borders of minus 1 minus x squared until 1 minus x squared square root. This equals 1 over 2 pi. We can take this out. We have the integral minus 1 to 1. Then we have integral dx times x, and then we have here now this in the two borders, 1 minus x squared, the square root, but we have to square it again, minus minus 1 minus x squared squared, but this here cancels each other, so this is 0 and this is 0, and from this we obtain that the covariance of x and y equals 0. So here we have a case where the covariance is 0, but the random numbers are not independent. So as another example where we have a 0 covariance but no independence. Okay, that were just 2 worked out examples. So the video was getting a bit long, I see, but I wanted to show you the examples. And now we have everything to go to processes which depend on time. Okay, thank you.